We have talked about conservative forces and how they relate to potential energy. There are non-conservative forces for which work depends on the path taken. Friction is a good example of a non-conservative force. Work done against friction depends on the length of the path between the starting and ending points, so there is no potential energy associated with friction. An important characteristic is that the work done by a non-conservative force adds or removes mechanical energy from a system. For example, friction creates thermal energy that dissipates, removing mechanical energy from the system. And even if this thermal energy is retained or captured, it cannot be fully covered back to work, so it is lost in this way. We have talked about conservation of mechanical energy when there are only conservative forces included. However, mechanical energy may not be conserved when non-conservative forces act. For example, in a system with only conservative forces, when a rock is dropped onto a spring, its mechanical energy remains constant. However, when the same rock is dropped onto the ground, it is stopped by non-conservative forces that dissipate its mechanical energy as thermal energy, sound, and surface distortion. The rock has lost mechanical energy. When both conservative and non-conservative forces act, we will see that although the mechanical energy is no longer conserved, the work done by non-conservative forces equals the change in the mechanical energy of a system. Since the work energy theorem states that the net work on a system equals to the change in its kinetical energy, and this net work is the sum of the work by non-conservative forces plus the work by conservative forces, so that we have WNC, work by non-conservative forces, plus WC, the work by conservative forces, equals to the change in kinetic energy. Considering this example in which a person pushes a crate up a ramp and is opposed by friction, there are 4 forces acted on the crate. The normal force does not do any work. The gravitational force is a conservative force, and its negative work on the crate results in a gain of the gravitational potential energy. Both the push force and the friction are non-conservative forces. Generally, we have work done by a conservative force related to the potential energy. Substituting this equation into this one, and we can get WNC equals to change in kinetic energy plus change in potential energy. This equation means that the total change in mechanical energy is exactly the amount of work done by non-conservative forces. In this case, the work done by the person minus the work done by friction is the change in the total mechanical energy. From the expression of W and C, we have this equation. If W and C is positive, then the total mechanical energy is increased, like the case in this figure. If W and C is negative, then the total mechanical energy is decreased. If W and C is 0, then the total mechanical energy is conserved. Let's look at this example together. When a baseball player slides to a stop on level ground, friction stops the player by converting his kinetic energy into other forms, including thermal energy. The work done by friction is W and C equals to minus Fd. Using this equation, since the baseball player has no potential energy and his final kinetic energy is 0, so that only the initial kinetic energy and the work done by friction are included. The distance d equals to 2.60 meters. We have been dealing with mechanical energy and energy transferred via work done by non-conservative forces, but energy takes many other forms such as thermal energy. In order to write a general statement of the conservation of energy, we put all other forms of energy into one single group called other energy, OE. Then we can state the conservation of energy in equation form as this one. All types of energy and work can be included in this very general statement of conservation of energy. In previous example, when there were only mechanical energy and non-conservative forces included, the term OE was constant, and so it's subtracted out and was not directly calculated. There are many examples of these other forms of energy. Electric energy to run all the machines, chemical energy from gasoline or food, thermal energy due to temperature, radiant energy, and nuclear energy. The transformation of energy from one form into another is happening all the time. Even though energy is conserved in an energy conversion process, the output of useful energy to work will be less than the energy input. The efficiency, EFF, of an energy conversion process is defined as useful energy or work output divided by the total energy input. Here are some efficiencies of mechanical devices and human activities. Let's look at some problem-solving strategies useful whenever you deal with energy. You may find these strategies are quite similar to the general problem-solving strategies presented earlier for kinematic and dynamic problems. First of all, determine the system of interest and identify known quantities and the quantities to be calculated. A sketch will help, And I will encourage you to draw a free body diagram whenever there are forces included in the problem. Then, we need to examine all the forces involved and determine whether the forces are conservative forces, thus related to potential energies, or some are non-conservative forces. If all the forces are conservative forces, then you can apply conservation of mechanical energy simply in terms of potential energy and kinetic energy. On the other hand, if some of the forces are non-conservative forces and do not have an associated potential energy, or if there are other energies that are not easily treated in terms of force or work, then the conservation of energy law in its most general form must be used. You can always simplify the equations before solving for the unknown quantity. For example, we can set the initial or final height to be 0 so that one of the gravitational potential energy can be 0. Finally, as always, we need to check the answer to see if it is reasonable.